Deep in the tropical north of Australia sits one of the strangest mineral discoveries ever made on the continent. Beneath what today is part of Kakadu National Park, geologists uncovered a deposit so large it helped place Australia on the global nuclear fuel map. But what makes the Ranger uranium deposit unusual isn't just its size, it's the company it keeps underground. Because this uranium deposit occurs in the same geological system that also hosts gold. That combination is extremely rare. Around the world, most uranium deposits and most gold deposits form in completely different geological environments. Uranium typically forms in basins where oxidized fluids move through porous rocks, while gold tends to form in hot hydrothermal systems associated with faults and tectonic compression. Yet, in the ancient rocks of northern Australia, the two systems overlap. In fact, some nearby uranium deposits contain measurable gold grades, and the alteration minerals that formed around the uranium look remarkably similar to those that form around gold deposits. Even stranger, the uranium deposit sits just below a massive geological boundary, an unconformity. An unconformity is a gap in the rock record where millions of years of erosion removed older rocks before younger sediments were laid on top. These boundaries often become highways for mineralizing fluids. At Ranger, that boundary became the focal point for one of the most significant uranium discoveries in Australian history. And when the deposit was discovered in 1969, it didn't just reveal a new mineral resource, it forced Australia to rethink uranium mining entirely. The Ranger deposit lies within a geological region known as the Pine Creek Orogen, an ancient belt of folded and metamorphosed rocks that formed roughly 2 billion years ago. The word orogen simply means a mountain building belt, a place where tectonic plates once collided and squeezed rocks deep underground. Those ancient collisions created a complicated stack of rock layers, faults, and shear zones. A shear zone is a fracture where rocks have slid past each other under pressure, often forming a pathway for hot fluids. These pathways are extremely important in geology because they allow metals to move through the crust. At Ranger, the basement rocks consist mostly of metamorphosed sedimentary layers belonging to the Cahill Formation. These rocks began life as muds, sands, and volcanic sediments deposited in ancient seas more than 1.8 billion years ago. Over time, they were buried, heated, and squeezed until they transformed into schists and other metamorphic rocks. Above them lies a completely different unit, the Kombolgie Formation. These are thick layers of quartz-rich sandstone deposited around 1.65 billion years ago after the older rocks had already been uplifted and eroded. The boundary between these two rock packages, the unconformity, is the key to understanding Ranger. For a long time, geologists believe uranium deposits here formed after the Kombolgie sandstones were laid down. The idea was simple: groundwater circulating through the porous sandstone dissolved uranium from the basement rocks, then carried it downward until it encountered chemically reducing rocks in the basement. When oxidizing fluids meet reducing minerals like sulfides or graphite, uranium drops out of solution and crystallizes as minerals like uraninite. But Ranger complicates that story. Radiometric dating, a method that measures radioactive decay to determine the age of minerals, suggests the uranium mineralization at Ranger may have occurred around 1.74 billion years ago, which is slightly older than the Kombolgie sandstones themselves. If that age is correct, it means the uranium may have formed before the famous unconformity even existed. This has led many geologists to propose a more complicated model involving multiple mineralizing events. The story likely begins around 1.8 billion years ago, during a period of tectonic activity in the Pine Creek Orogen, known as the Shoebridge Event. During this time, hot hydrothermal fluids circulated through the crust along major shear zones. Hydrothermal fluids are simply hot, mineral-rich water that moves through fractures in the earth. Those fluids altered the rocks around the Ranger's shear zone, replacing existing minerals with a new suite of alteration minerals including chlorite, white mica, quartz, and monazite. Chlorite is a green iron-rich mineral that commonly forms when hot fluids alter volcanic or sedimentary rocks. White mica is a fine-grained sheet mineral often associated with hydrothermal systems. This alteration stage is important because it prepares the rocks for later mineralization. It created chemically reactive zones that could trap metals. Interestingly, the alteration minerals found here are almost identical to those seen in nearby gold deposits. That's one reason researchers believe the uranium system may have developed within an earlier, gold-forming hydrothermal environment. Later, oxidizing fluids carrying dissolved uranium moved through the same structures. These fluids were likely highly saline brines derived from nearby sedimentary basins. When those oxidized uranium-bearing fluids encountered reducing minerals in the basement rocks, uranium precipitated as uraninite, a dense black mineral composed primarily of uranium dioxide. The The resulting ore bodies form within fault zones and breccias. Breccia is a rock made of broken fragments cemented together, often produced when faults fracture rocks during tectonic movement. These broken zones are ideal traps for mineralizing fluids because they allow fluids to flow easily while also providing abundant surfaces where minerals can precipitate. What makes the story even more intriguing is that Ranger sits within a broader cluster of uranium deposits known as the Alligator Rivers Uranium Field, one of the richest uranium provinces on Earth. Within a relatively small area, several major deposits occur along the same structural corridors in the Pine Creek Orogen. These deposits all formed in roughly the same geological environment, ancient metamorphic rocks sitting beneath the Kombolgie sandstones, and cut by major shear zones that allowed fluids to circulate through the crust. But each deposit records a slightly different history of fluid flow and mineralization, suggesting the region was repeatedly reactivated by tectonic events over hundreds of millions of years. In other words, the Alligator Rivers Field isn't the product of a single uranium-forming event, but a long-lived geological system that kept reopening pathways for mineral-rich fluids deep beneath northern Australia. At Ranger, these structures created two main ore bodies known as Ranger No. 1 and Ranger No. 3. Mining began in 1980 with the development of a large open pit. Over the decades that followed, the mine became one of Australia's most important uranium producers. In terms of ore grade, Ranger is not among the highest grade uranium deposits on Earth, but it is still significant. The average ore contains roughly 0.25 to 0.30% uranium oxide. That means a ton of ore typically contains around 2.5 to 3 kilograms of uranium oxide. To put that in perspective, a ton of typical gold ore might only contain a few grams of gold. Uranium deposits are measured in kilograms per ton rather than grams because the element is more abundant in these systems. Over its lifetime, Ranger produced more than 110,000 tonnes of uranium, making it one of Australia's largest uranium mines. But the significance of Ranger isn't just about production. Its discovery fundamentally changed the way Australia regulates uranium mining. The deposit lies within land traditionally owned by the Mirarr people, and its proximity to what would later become Kakadu National Park triggered one of the most important environmental inquiries in Australian history. The Ranger Uranium Environmental Inquiry established strict environmental standards and consultation processes that still influence uranium mining policy today. In other words, the geology of Ranger didn't just reshape the landscape underground, it reshaped the way Australia approaches mining, environmental protection, and Indigenous land rights. And the geological mystery of the deposit still continues to fascinate researchers. Because Ranger sits at the intersection of multiple mineral systems, uranium, gold, and hydrothermal alteration associated with ancient tectonic events, that overlap is extremely unusual. Most unconformity-related uranium deposits around the world, particularly those in Canada's Athabasca Basin, contain little or no gold. But in the Pine Creek Orogen, uranium deposits commonly occur in regions that also host gold mineralization. This suggests that the hydrothermal systems responsible for gold may have played a role in preparing the structures that later trapped uranium. In other words, the crust beneath northern Australia may have been preconditioned by earlier tectonic activity, creating the perfect geological trap. And that's what makes Ranger so fascinating. It's not just a uranium deposit, it's a snapshot of a complex geological history spanning hundreds of millions of years. From ancient mountain building to hydrothermal alteration, from basin formation to fluid migration through deep crustal faults. Each of those events left its mark in the rocks beneath Kakadu, and together they created one of the most unusual mineral deposits on the continent. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.